From work to energy. If you have a height, then you have gravitational potential energy. If you have a speed or velocity, then you have kinetic energy. If you're in orbit, you have gravitational potential energy. If you have a spring, you have elastic potential energy. If there's a resistive force like friction or drag, work is being done to remove energy from the system. So we're going to include FD cosine theta, or FF times D cosine theta. If you have at least two of those things, quantities, height, speed, orbit, spring, resistive force, if you have at least two of them, then we should be using conservation of energy. Remember, when we use conservation of energy to define our system, energy is always traceable. And if we're deriving something using conservation of energy, then we need to start off with all of the energy in the beginning equals all of the energy in the end. You might do sigma E sub I equals sigma E sub F. You might do TME sub I equals TME sub F. Whatever it is, just make sure that you show that you're using conservation of energy. We're going to use U sub little g when we're near the surface of a planet or star or asteroid. And we're going to use U sub big G when we're dealing with big objects in space. Big G, big stuff. UG will always work. It just turns out that U sub little g is usually a bit more convenient for us. U sub g is negative because when two objects are infinitely far from each other, they are no longer within each other's gravitational field. So F sub big G is not doing any work. Remember that if we set our reference point way out at infinity and we integrate from infinity to 0, that's what's going to give us that negative sign. For U sub g, you can set the reference height, not at infinity, but instead you can set it anywhere that's useful to you and make that h equals 0. Usually we're going to make that the lowest point in our path. Conservative forces are forces with an associated potential energy. Fg has Ug, Fs has Us, F sub big G has U sub big G. Those are our conservative forces. If a conservative force is acting within a system, then energy is conserved. If a non-conservative force is acting within a system, energy is changing within that system. But outside of that system, it's still able to be conserved. Remember, energy is always traceable. So we start off with our statement of conservation of energy. Here I did TMEI equals TMEF. And let's say we have gravitational potential energy in the beginning equals final kinetic energy plus some work done by a non-conservative force. Think about your bar charts. The total amount on the left should equal the total amount on the right.